Hello YouTube. At the request of one of my viewers, I'm going to make a live implementation of the algorithm needed to compute fractal images of the Mandelbrot fractal. So I'm going to just rush this and hope it'll turn out alright. So first thing I'm going to do is import a few things. I want the colors in the image to be a particular shade. So from colors is import HSV to RGB, because I know a few things about fractals of this nature. I know the images can be pretty dark if the depth is set too high. Pygame, and from Pygame import everything. That's for actually outputting the images. So the first thing we're going to need is the computation for the complex numbers. So define computation of the complex number z, and there's a maximum depth associated with this. So compute z. Let's see. We need to know the iteration number per pixel per z. So I, z0 is z0 and 0. So I is the number of iterations, z0 is the starting point, and we know that from while I smaller than m, we'll need to compute. So while there's still iterations to be computed, and while z is within the Mandelbrot set, so that means let's see, that the computation for this one is z0 times z0 plus z1 times z1 is smaller than 2 times 2. So while the orbit, while the radius is still smaller than 2. Compute these z values. So we'll need two things for the z value. The complex number has to be squared. So let's say z is a tuple. We will require the new z to be the squared value of its current value. So z0 times z0 minus z1 times z1, comma. If you remember complex values being squared, you take x and y, y times the imaginary unit. So this is x squared times a plus y squared. And I say plus because I squared is, of course, the imaginary unit squared is, of course, minus 1. So these are the real parts, and here come the complex parts, which is the middle term of the squared of a squared value. That is 2 times a times b, where a and b are, of course, the real part and the imaginary part, 1. So this is the complex number, and we'll add the z0 value to this. So let's see, z plus z0 real part plus z0 imaginary part. I plus is 1, and then we should return the z value. So this is for computing the color of a pixel. Now we need to feed this function some pixels and return the pixels to the image. So def mandel, and what we need here is user input for the image. So first of all, we need to know the size, which is the width and the height, and for what we want to display in this image, we need to know the center and the x range and the y range. Let's just call that x and y. Yeah, so this is my regular way of doing things, programming. So the image is an empty array of zeros for I in width it's 0 for j in range height. So just declaring an empty array. For I in range x. No wait. For I in range w. For j in range h. So for every pixel, img y I and j is compute, and we will need two things over here. We will need to put the number in and the max depth. So we still need to know the max value, max iterations. Compute the pixel and the pixel compute complex number, and the complex number is of course the center minus the range. Let's see, into plus the range times I over width. Yeah, that's it. And of course we do this for the y value as well, which is to say h and j and y and 1, the center value 1. So yeah, this is the color. Oh, we need to not return z. We need to value y over m, because we will need values between 0 and 1. Yeah, that's the Mandel. Oh, there's an optimization thingy going on here. The image is symmetrical in the j range, so I'm gonna just cut this number in half, add 1 for odd numbered resolutions, and I'm just gonna mirror these colors. This is gonna be h minus j plus 1. No, wait, minus 1. Yeah. So this is for mirroring the image in the vertical direction, cutting the computations in half. Yeah, that's correct. I think. We'll see. Let's see. That's the I will need to return the image. Now, to actually export the image, def export. This will take an image and a file name, and for let's call a surface first. Surface is pygame point surface. This thing needs a size, so this is I forgot if it takes this or this. A size, that's all it takes, and this is the length of the image, comma the length of the image 0, so that's the height. Spent fill, I just need it to be black, or an initial color. This is black. Well, for every pixel in the image, we will need to compute a color. Damn it. Call is, let's do something. Oh yeah, this is where I need the HSV to RGB, which is let's say HSV to RGB, because I like the color transition using this function, which is imij, comma 1, comma 1. So this is just a saturated color. Now this will return a color with values between 0 and 1, so I need to scale this. Scale color 255, comma the color there. Now this function is not yet present, so we need the scc is lambda of a scale value and a color, and we need it to return let's see, s times c0 comma s times c1 comma s times c2. Of course this can be made more efficient. So the color is now determined. We need to set the color to the surface as point set at I comma j comma col, and then we need to save the image to the file name, and that's it. So that's the entire thing. Now there's a lot of lots of improvements to be made. I won't expand upon. Let's just render an image. So first thing, we need an image. Mandel. The arguments here are the width and the height, 320 times 240. The center, which is minus 1, comma 0. I just happen to know this might be a good value. The x range is 3, the y range is 2, and the max depth is 25. Not a really high number. Export the image to let's say fractal point png. Now let's see. Yeah, it dies. Z0. And there we go. And this is the resulting fractal. So let's see. I can render it in another color just for your entertainment purposes. And I'm not going to use this color. I'm going to use a different color. Just black and white will do. So 255 comma times image ij. This will render it black and white. Oh, need to insert commas more often. The image. There we go. So that's the Mandelbrot fractal. Not a really challenging implementation, but there's a lot of room for improvement. So have fun with that. Free source code, of course. So yeah, I hope this the viewer who requested this video likes it, and I guess I'll see you guys in the next video. Bye.